everyone. Uh, this is my next assignment submission. I have uploaded all my collabs here in this deep learning training design space folder. My all the collabs are uploaded here, and the videos links will be added in this video folder. So let's start with our first collab. Um, which is activation functions tutorial. I'll just quickly open it. So in this notebook we will take you through the fascinating world of activation functions, the component that gives neural network their power to learn complex patterns. So what we will learn here, why activation functions are essential in neural networks, the mathematics behind each activations, how to choose the right activation for your task, modern activations used in state of arts and models. So this is what we are going to learn. Uh, so let's move forward. In this cell, I'll set up the environment. I import the NumPy for numerical operations, Matplotlib for plotting the graphs, PyTorch for building neural network, and scikit-learn for generating the datasets. Then I suppress the warning so that output is clean. I also set a random seed for NumPy and PyTorch. This ensures reproducibility, meaning the same results are obtained every time when we run the notebook. Finally, I configure plotting parameter like figure size and font size to make visualizations clear. And then let's move forward. So this cell explains the core motivation behind the activation functions. I show mathematically that stacking linear layers still results in a linear transformation. So even a deep network without activation function behaves like a simple linear model. This means it cannot learn complex patterns like XOR or curved decision boundaries. So activation functions are required to introduce nonlinearity to our network. So let's move forward. So in this cell, I'll visualize the limitations using datasets. First, I plot a XOR problem and show that no straight line can separate the classes. So see here we have plotted it, and no separate line can straight line can separate these two classes blue and red. That's what I am doing here. This is the first problem, and then I also generate the moons dataset and circle dataset using scikit-learn and plot them. These datasets require a curved decision boundary. So for moon also it will require a curved decision boundary to separate them, and for circle also, which linear model cannot learn. So visually reinforces why activation functions are necessary. Now here I define what activation functions um, does in a neural network. So after computing the linear transformations, the wx plus b, we apply a function sigma to introduce nonlinearity, and it also lists desirable properties such as being nonlinear, differentiable for backpropagation, avoiding saturation to prevent vanishing gradient, and being computationally efficient. So these are the properties. Uh, Now moving towards the next cell. This cell introduces sigmoid and tanh activation functions. Sigmoid maps input between 0 and 1 and make it useful for probabilities, while tanh maps minus 1 and 1, making it 0 centered. So however, both the functions saturate at extreme values where their gradients become very small, and this leads to vanishing gradient problem during the training of deep neural network. So this is sigmoid uh, derivatives, and this is tan h, and this is tan h derivative. We have plotted this. So when gradients are less than 1, they shrink exponentially through the layers, and sigmoid max gradient 2.5. After 4 layers it becomes 0.004. This makes deep neural network nearly impossible to train. So in this cell, um, I have plotted four graphs for sigmoid derivative and tanh for derivative. The derivative plots, we can clearly see the gradient approaches to zero at the extreme values. Um, these extreme values, it is reaching to zero. This explains why gradients shrink as they propagate backward through layers and making the learning very slow in deep networks. So this cell introduces ReLU with which stands for rectified linear unit. So the code, it simply returns 0 for negative input and keeps positive inputs unchanged. This avoids vanishing gradients on positive sides and is computationally very efficient. However, it introduces a new issue called dying ReLU problem, where neurons can stop updating if they consistently receive negative inputs. So in this cell, I implement ReLU and its derivative and then visualize STEM. ReLU plot shows zero output for negative values, and linear growth for positive inputs. Derivative is 0 for the negative. Uh, the derivative is 0 for the negative inputs, while the derivative is 1 for positive inputs. And then I simulate the dying ReLU problem by feeding mostly negative values uh, ReLU, into ReLU. As a result, the output becomes 0, meaning all the neurons effectively stops learning. So this cell introduces improved versions of ReLU. Leaky ReLU allows a small non-zero slope for negative inputs, which prevents neurons from dying completely. Pre-ReLU is similar but learns this slope during training. Uh, LU introduces a smooth exponential curve for negative inputs, improving the gradient flow, and SELU further scales their behavior to maintain the stable and variance during training. Cell 11. In this cell, I implement these variations using NumPy, and then I plot all the activation functions together to compare their shapes, especially how they behave for negative inputs. I also vary parameters like alpha in leaky ReLU to show the slope changes. And finally, to summarize the I include this table to summarize their properties like smoothness, computation cost, whether they suffer from dead neurons. So this is ReLU family comparison. The red one is ReLU, the blue is leaky ReLU, this is LU and this is SLU. We can see it's 0 for ReLU and others are having some values. Leaky ReLU with different values of alpha, we can see it's changing, and LU is smooth at x is equals to 0, and this is the comparison. So in ReLU we have dead neurons problem, but this other three we don't have the problem. ReLU is not zero centered, but these two are. ReLU is not smooth, but LU and SLU are. But ReLU and leaky ReLU are fast compared to others. Now, this cell introduces modern activation functions like JLU, swish, and mesh. These functions are smoother than ReLU and allow small negative outputs. JLU is widely used in transformer models like BERT, GPT, Swish model, and Mesh are also designed to improve the gradient flow of model performance. So in this code, I implement JLU, Swish, and Mesh, and then I plot them along with ReLU to compare their shapes. I use zoom into the negative region to highlight how these functions differ from value and which completely cuts off negative value. Finally, I included a table. Um, Finally, I included a table showing the which activation functions are used in popular deep learning models. So this is the graph and this is the zoomed negative. So this was our main graph, and this portion we have zoomed in, this negative one, and we can see this is our ReLU, this is GeLU, and this is swish for the negative value outputs. So, and this is the activation functions and where they are used. Now, this cell explains the activation functions used in the output layers. Sigmoid is used for binary classification to produce probability between 0 and 1. For softmax is used for multi-class classification where it converts logics into a probability distribution that sums to 1. For regression, no activation is used, so output remains continuous value. In this cell, I demonstrate the output activation using some example values. I apply sigmoid to convert logics into probabilities and visualize the threshold. Then I apply the softmax for set of classes scores and show how they become normalized probabilities. Finally, I included a table that maps different machine learning tasks to appropriate activation functions and loss functions. So this is what we are doing here, and we can see in the last we have this task, output activation we will use, the loss function we will use, and examples where they are used. Now moving forward, this cell provides practical guidelines for choosing activation functions. For example, GeLU is commonly used in transformers, and ReLU or CeLU is used for CNNs, and ReLU and CeLU are used for MLP variants also. So in this section, it helps us to connect theory with the real world model design. So in this cell, I first generate a moons dataset and using scikit-learn and convert it into a PyTorch tensors. Then I define a neural network class with multiple layers where the activation function can be selected dynamically, and I also define a training function that trains the model using Adam optimizer cross entropy loss while tracking loss and accuracy. And then I train the model using different activation functions and store their results for comparison. So we can see the final accuracy is the highest for ReLU and the accuracy is decreasing for other models. Now in this cell I visualize the results. I plot a training loss curve to compare how fast each activation learns, and then I generate a grid of input points and use the trained models to predict the outputs, and which allow me plot a decision boundary, and finally I compare the accuracy of all the activation functions using a bar chart. So we can see this is the training loss computations. The loss is maximum in the sigmoid, whereas the minimum in the ReLU. You can see how leaky ReLU is 98% accurate. In LU we can see some data points are clustering. Sigmoid is a straight line which is not able to cover proper points, and this is the final accuracy plot. So this cell finalizes the summary takeaways. The activation function introduced nonlinearity. ReLU made deep learning practical, and modern equations like GELU are widely used today. It also provides a quick reference and shows the evaluation of activation functions over time. And yeah, that's it. So this was the complete explanation of my notebook covering both theoretical concepts and practical implementations of activation function. Thank you so much.